In the Nevada desert in 1963, American engineers embarked on something extraordinary, a program to build nuclear rocket engines that could revolutionize space travel. The NERVA program, Nuclear Engine for Rocket Vehicle Application, successfully proved that atomic power could propel spacecraft with efficiency that chemical rockets could only dream of. They achieved specific impulse of 811 seconds, nearly double that of the best chemical engines, with later designs targeting 825 seconds. Then, in 1973, after spending nearly $2 billion, they shut it down and buried the test engines at the Nevada test site, literally interring America's nuclear propulsion dreams in the desert sand. For 50 years, those engines remained buried, both physically and in the national consciousness. Nuclear thermal rockets became a taboo subject, associated with Cold War paranoia and environmental fears that no politician dared resurrect. But in 2021, everything changed. China announced its own nuclear thermal rocket program, with Dr. Zhang Yulin providing a timeline for crewed Mars missions using this technology by the 2040s. Suddenly, America's abandoned technology became a critical national security vulnerability. Now, the United States is scrambling to resurrect what it buried decades ago through DRACO, the Defense Advanced Research Projects Agency's ambitious gamble to reclaim American dominance in space before it's too late. The question isn't whether nuclear rockets will revolutionize space travel. The question is, which flag will they carry? To understand why America is frantically reviving this technology, we need to confront the ghost that still haunts it, the spectacular rise and mysterious fall of NERVA. The program was formally established in 1963, evolving from the earlier Project Rover after NASA took a leading role in developing nuclear thermal propulsion for space applications. It was the golden age of American space ambition, when anything seemed possible, and the race to the moon demanded technologies that pushed every boundary. The engineers working on NERVA weren't just building rocket engines, they were crafting the keys to the solar system, and it worked. The NERVA A2 test achieved that remarkable 811 seconds of specific impulse, proving the fundamental concept was sound. To put that in perspective, imagine you're driving two cars across the country. One gets 25 miles per gallon. That's your chemical rocket. The other gets 50 miles per gallon. That's NERVA. You'd reach your destination using half the fuel, or you could go twice as far on the same tank. In space, where every kilogram of propellant costs thousands of dollars to launch, that difference isn't just significant, it's revolutionary. But three fatal flaws conspired to kill the program. First, costs were escalating dramatically. The Vietnam War was devouring the federal budget, and NASA's priorities were shifting away from ambitious deep space missions. By the time NERVA was terminated in 1973, it had consumed nearly $2 billion, an astronomical sum that became impossible to justify. Second, there was no committed mission that actually required nuclear thermal propulsion. The Apollo program was winding down, and the grand visions of Mars expeditions that might have justified NERVA's expense evaporated in the political realities of the early 1970s. Third, public and political concerns about nuclear safety and environmental risks grew louder, especially with no clear near-term application to show for the investment. When the program ended, those test engines were buried at what is now the Nevada National Security Site. It was both a practical disposal measure and a symbolic burial of America's atomic space dreams. For half a century, they lay there, forgotten monuments to abandoned ambition, until China forced America to remember. The announcement of China's nuclear thermal rocket program in 2021 sent shockwaves through the American space establishment. Here was a geopolitical rival openly pursuing the same technology that the United States had perfected and then abandoned. Dr. Zhang Yulin's timeline, pointing to the 2040s for crewed Mars missions, suddenly made America's buried engines look less like wise restraint and more like strategic negligence. The question became urgent. If NERVA was so promising, why did it take a rival superpower to force America's hand? The answer lies in what makes nuclear rockets so powerful, and why that power is worth resurrecting. despite the ghosts of the past. The fundamental physics of nuclear thermal propulsion are elegantly simple, even if the engineering is brutally complex. Instead of burning chemical fuel, which is really just rearranging molecular bonds to release energy, a nuclear reactor uses atomic fission to generate heat directly. That heat is transferred to hydrogen propellant, raising it to extreme temperatures exceeding 2,500 degrees Celsius. The superheated hydrogen then expands through a nozzle and rockets out at tremendous velocity, producing thrust. No combustion required, just pure thermal expansion driven by nuclear fire. This is where specific impulse becomes critical. Think of specific impulse as the miles per gallon rating for rocket engines. It measures how efficiently an engine converts propellant into thrust chemical rockets, limited by the energy available in molecular bonds, top out around 450 seconds. The DRACO program is targeting around 900 seconds, essentially doubling the efficiency of the best chemical systems. It's not an incremental improvement, it's a revolution. What does that mean in practical terms? Consider a Mars mission. With chemical propulsion, the journey takes 6 to 9 months of continuous exposure to cosmic radiation, zero-gravity muscle atrophy, and psychological stress. Every extra day in transit increases the risk to the crew and the complexity of life support systems. Nuclear thermal rockets could potentially cut that transit time to as little as 3 to 4 months, about half the duration. That's not just faster, it's fundamentally safer. Radiation exposure is reduced. Psychological strain is lessened. The mission becomes more survivable. But the strategic implications extend far beyond Mars. Whoever controls nuclear propulsion controls the ability to move rapidly anywhere in cislunar space. The vast region between Earth and the Moon that's becoming the new strategic high ground. They can respond to threats, inspect satellites, and establish presence at economically valuable locations like Lagrange points. They can reach asteroid resources that could be worth trillions of dollars. In short, nuclear thermal propulsion isn't just about exploration. It's about power projection in the ultimate high ground, space itself. Yet for all its promise, nuclear propulsion presents a central engineering paradox. To achieve these performance gains, DRACO's reactor must operate at temperatures that would melt most known materials, while maintaining absolute containment of radioactive material. This is the challenge that defeated NERVA engineers working with 1960s technology. The reactor core is, quite literally, a miniature sun that must be controlled with absolute precision. One failure could scatter radioactive material across orbit, or, worse, back to Earth. The heart of the problem is the reactor core itself. NERVA used solid uranium fuel elements coated in graphite. At the extreme temperatures required for peak performance, these fuel elements degraded rapidly. The graphite would erode, the uranium would crack, and radioactive particles would contaminate the exhaust. Engine lifetime was limited, and each test left behind a trail of radioactive debris. For a technology that needed to operate for hours during an interplanetary mission, this was unacceptable. Modern materials science is providing answers that the NERVA generation could never access. The advanced nuclear fuel being developed for the DRACO reactor is high-assay low-enriched uranium, or HALEU. This fuel can withstand far higher temperatures than NERVA's graphite uranium elements while maintaining structural integrity. It's a critical breakthrough that addresses one of the fundamental limitations that plagued the original program. But advanced fuel is only part of the solution. There's another insidious problem: hydrogen embrittlement. Liquid hydrogen, the propellant of choice because of its low molecular weight and high exhaust velocity, is extraordinarily reactive. At the molecular level, hydrogen atoms are so small they can actually penetrate the crystalline structure of metals. Once inside, they disrupt the atomic bonds that give metals their strength, causing catastrophic brittleness. A component that looks perfectly sound can suddenly shatter under stress because hydrogen has invisibly compromised its structure from within. This is where modern computational tools provide an advantage that NERVA engineers could only dream of. Computational fluid dynamics, CFD, allows supercomputers to simulate millions of scenarios, optimizing reactor geometry and predicting failure modes before building physical prototypes. Instead of expensive and time-consuming test and iterate cycles with actual hardware, engineers can now explore the entire design space virtually. They can model how hydrogen flows through the reactor core, where hotspots might develop, which materials will survive longest, and how to maximize performance while minimizing risk. It's the difference between exploring a dark cave with a flashlight and having a complete three-dimensional map before you enter. The progress has been remarkable. In recent high-fidelity ground tests, the DRACO reactor containment system successfully demonstrated containment integrity under simulated operational conditions, a critical milestone that addresses one of the central safety concerns that doomed NERVA Zero measurable leakage: perfect containment. But here's the uncomfortable truth. These tests were conducted in controlled ground facilities, not in the violent environment of launch, where a rocket experiences crushing acceleration, or in the thermal extremes and radiation environment of space. The real test is still to come. Even the most brilliant reactor design is useless if the public won't accept it. This is where NERVA's ghost still haunts the program most powerfully. The very word nuclear carries baggage, decades of association with weapons, accidents, and environmental contamination. For DRACO to succeed, it must overcome not just technical challenges, but deep-seated public fears and political resistance. This is perhaps the most difficult engineering problem of all: engineering public trust. The radiological risks fall into three scenarios. First, launch failure. The rocket explodes or crashes before the reactor is activated. Second, operational accident. The reactor malfunctions while operating in space. Third, re-entry. A spent reactor returns to Earth's atmosphere. Each scenario carries different risks and requires different mitigation strategies. DRACO's safety approach addresses the launch failure scenario directly. The reactor remains cold, non-critical, until the spacecraft reaches high orbit, well above the atmosphere. This means that if a launch fails, what crashes back to Earth is non-radioactive uranium fuel, not highly radioactive fission products. It's still hazardous material, but it's not the catastrophic dispersal of intensely radioactive debris that nightmares are made of. The reactor only becomes hot once it's safely in space, where a malfunction wouldn't threaten Earth's surface. For spent reactors, the solution is the orbital graveyard concept, boosting them into stable disposal orbits that won't decay for thousands of years, far longer than the radioactive half-life of the materials involved. By the time these orbits naturally decay, the radioactivity will have diminished to background levels. It's not a perfect solution, but it's a manageable one that balances risk against strategic necessity. There's an economic argument that makes DRACO more viable than NERVA ever was. While NERVA consumed nearly $2 billion in the 1970s, the projected total cost for the DRACO demonstrator is significantly lower, thanks to advances in materials, computational modeling, and manufacturing. Modern tools allow engineers to accomplish in months what took NERVA teams years, and at a fraction of the cost. The program is expensive, certainly, but it's no longer the budget-devouring monster that NERVA became. Yet there's an uncomfortable geopolitical dimension to the safety debate. China's authoritarian system allows them to pursue high-risk, high-reward technologies without public debate, environmental review, or democratic accountability. They don't need to convince skeptical voters or navigate complex regulatory frameworks. They can simply decide and execute. This potentially gives them a decisive speed advantage in development, even if American technology is ultimately superior. It's a stark reminder that in the race for transformative technologies, democratic transparency can be both a strength and a vulnerability. The clock is ticking, and the timeline is unforgiving. China is constructing nuclear thermal rocket testing facilities in Inner Mongolia, visible evidence of their commitment to this technology. Dr. Zhang Yulin's timeline pointing to the 2040s for crewed Mars missions puts immense pressure on the United States to regain the initiative. DRACO's planned schedule calls for ground tests by 2026 and an in-space demonstration by 2027. It's an aggressive timeline that leaves little room for error or delay. What's at stake extends far beyond national pride. If China achieves operational nuclear propulsion first, they could establish facts on the ground, or rather, in space, before the United States can respond. They could claim strategic positions at Lagrange points, establish dominance in cislunar space, and potentially reach Mars first. The nation that controls nuclear propulsion will write the rules for humanity's expansion beyond Earth. They'll determine who has access to asteroid resources worth trillions of dollars. They'll control the strategic high ground that makes low Earth orbit look like a shallow puddle by comparison. This raises a profound question about democratic societies and technological competition. Can open societies, with their debates and accountability and safety reviews, compete with authoritarian regimes that face no such constraints when developing transformative technologies? The race to develop nuclear thermal rockets is becoming a test case for that question. It's not just about engineering anymore. It's about whether transparency and caution are luxuries we can afford when rivals are sprinting ahead, unburdened by public scrutiny. We began with a question. Why is America resurrecting a technology it buried 50 years ago? The answer reveals a profound transformation in how we understand space power. Nuclear thermal propulsion isn't just about faster trips to Mars. It's about who controls the strategic high ground of cislunar space, who can access the vast mineral wealth of asteroids, and ultimately, who writes the rules for humanity's expansion beyond Earth. The engineers of DRACO aren't just building a rocket engine. They're fighting to ensure that the values of open societies, international cooperation, and transparent science shape humanity's future in space, rather than allowing authoritarian control of the solar system's most transformative technology. The ghost of NERVA has been exorcised not through forgetting the past, but by learning from its mistakes. Modern materials replace fragile graphite. Computational models replace guesswork. Rigorous safety protocols replace Cold War hubris. The NERVA engines buried in the Nevada desert were monuments to abandoned ambition. But perhaps they were never really abandoned, just waiting. Waiting for the materials science to catch up. Waiting for the computational tools to mature. Waiting for the geopolitical necessity to become undeniable. Those buried engines weren't failures. They were seeds planted in the desert, waiting for the right season to bloom. In the end, the race to develop nuclear thermal rockets isn't about America versus China or democracy versus authoritarianism. It's about whether our species will remain trapped in Earth's gravity well, taking months to crawl between worlds, or whether we'll finally grasp the key to the solar system, the power of the atom, harnessed not for destruction, but for the greatest journey in human history. The engine that wins this race won't just take us to Mars faster. It will determine who we become among the stars. Which engineering challenge do you think is the hardest to overcome? The physics of containing a nuclear reactor in space, the political challenge of gaining public acceptance, or the geopolitical race against rival nations? Let us know in the comments. And if you want to see how other Cold War space technologies are being resurrected for the new space age, check out our video on nuclear pulse propulsion, the insane concept that makes DRACO look tame by comparison. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.